This video is about reversible reactions and how they reach equilibrium, and also how the equilibrium can shift position. And that's something we talk about Le Chatelier's principle. So you've got an example of a reversible reaction here. You can tell it's reversible because it's got the reversible reaction sign saying that it can go both forward and backwards. So red and yellow can join to make blue, and blue can decompose into red and yellow. So both those reactions will be happening at the same time, all the time. Now what I've got here is a closed container. Okay, and that's very important for reaching equilibrium of reversible reactions, because neither the reactants, the red and yellow, nor the products, the blue, can escape from the system. And if it's in equilibrium, that means that the forwards reaction, red plus yellow makes blue, and the backwards reaction, which is blue makes red plus yellow, those will be happening at the same rate. So that's how things reach equilibrium, reversible reactions, when both the forwards and backwards reaction are occurring at the same rate, and when they're in closed apparatus so that the reactants and products cannot escape. And that means that if you leave this, even though red and yellow particles will be joining to make blue, and blue will be breaking apart to make blue, red and yellow, the amount of particles of each colour will stay the same. So I've got 10 blue, 10 red, 10 yellow. If I come back in 10 minutes, an hour, I'd still expect to have 10 blue, 10 red, 10 yellow. So that's equilibrium. So this is again the definition of equilibrium written down. Forwards and backwards proceed at exactly the same rate. No reactants or products can escape. And this is a graph for a reversible reaction between nitrogen and hydrogen to make ammonia. You can see we might start off with a lot more of the reactants and very few products, in fact 0 if we just put hydrogen and nitrogen together. And as that reaction starts, we'd expect, whether it's reversible or not, that the amount of nitrogen and hydrogen decreases and the amount of ammonia increases. If it was a non-reversible reaction, when that goes to completion, it might be the other way round, that you have none of one of the reactants left and only the products. But because it's reversible, it goes both ways. We end up at some point with a fixed concentration of each of these reactants and products. And that's called reaching equilibrium. Now the equilibrium position can be shifted. It can be shifted to the right, which means we have a higher yield of products. So if we go back to our example with the red plus yellow makes blue, this is now an equilibrium in a very different position. So the forwards and backwards reactions are still happening at the same rate. It's still a closed container, but I'm at equilibrium in a position where they've got very few red and yellow particles and a lot of blue particles. That means I've got a really high yield of the product, and the equilibrium has shifted all the way to the right. The forwards and backwards reactions are still happening at the same rate. To make this shift, I will have had to change the conditions. So it might be that the temperature in the container is different. It might be that the pressure in the container is different. It might be that when I started off, I added a lot more of the reactants, or I started off with a lot fewer reactants. Those are things that can shift the position. And we'll talk about how you can change the conditions to decide whether you want to shift it to the right or the left in a few moments. You can also shift equilibrium to the left, getting a lower yield, again by changing the conditions, but changing them in the opposite direction. So if you increase pressure to increase the yield, you decrease pressure to decrease the yield. And that varies a little bit from reversible reaction to reversible reaction. So you've got lots of red and yellow particles here, and a really low yield of the blue particles because the equilibrium is quite far to the left. Even though we've still got closed apparatus, we've still got forwards and backwards reaction happening in the same rate, it's still equilibrium, just in a different position. And if I come back from it a long time later, I'd expect to have the same proportions of red, yellow and blue. That's what equilibrium is. So changing that position of equilibrium, changing either the temperature, pressure or concentration. And we talk about Le Chatelier's principle. So if a system is at equilibrium, so that could be any of those pictures of the red, yellow and blue particles I just showed you, they're all at equilibrium, and a change is made to any of the conditions, then the system responds to counteract that change. So if I've increased the temperature, the system's going to respond in a way to try and cool the system down. If I've increased the pressure, the system's going to try and decrease the pressure. If I've increased, so for example, if I'd made the pressure higher by making the container smaller, the system would try and decrease the pressure by reducing the number of particles in the system. And if I add more reactants in, then the system's going to try and make more products, fewer reactants. If I take products away, the system's going to try and make more products, fewer reactants. And Le Chatelier's principle is used to predict the effect of changing conditions. So you can be given a reaction equation and asked, if I increase the temperature, what happens? If you decrease the pressure, what happens? If you add more reactants, what happens? And you predict that using Le Chatelier's principle, knowing that the system is going to respond to counteract the change that you have made. So, first one is if you increase pressure, which way does equilibrium shift? So I mentioned this before, we might have done that by making the container smaller. So to try and bring the pressure back down to the original level, we're going to need fewer particles. Now, if you look at this equation here, on the left-hand side there are 4 moles, on the right-hand side there are 2 moles. So by shifting to the right, the side with fewer moles, that means there will be less particles in the system and it will bring the pressure back down. So increasing pressure shifts it towards the side with fewer moles. In the equation at the bottom, there's 1 mole on the left and 2 moles on the right. So there are now more moles on the right. So increasing pressure will shift this equilibrium to the left, meaning a lower yield of products. So increasing the pressure would shift these 2 reactions in different directions. It would shift this reaction to the right with a higher yield of products, this reaction to the left with a lower yield of products. Increasing temperature, again the system's going to want to bring the temperature down, so it shifts in the endothermic direction to absorb some of that extra heat and cool the temperature of the system down. So the example of this that you are expected to know for your specification is this reaction, reversible reaction between hydrated and anhydrous copper sulfate. So hydrated copper sulfate is what you'll be used to seeing. It's blue. We've got some solid blue crystals here. But each copper sulfate molecule, you can see this little dot here, is joined to 5 water molecules. And when you heat that, it will absorb that heat, take it in, and the copper sulfate will separate from those water molecules, and you end up with this anhydrous copper sulfate. Anhydrous means without water, which is white. And that's a test used to detect the presence of water. So if you put anhydrous copper sulfate anywhere, if there's water, it will turn blue because it will join with that water, go in the reverse exothermic direction. So this is a reversible reaction. The forwards reaction is endothermic. That means if you increase the temperature, the equilibrium will shift to the right. You'll have more products and higher yield of anhydrous copper sulfate and water. If you decrease the temperature, it will shift in the exothermic direction towards the left. You'll have a lower yield of products. All reversible reactions have one endothermic direction and one exothermic direction. Sometimes the endothermic is forward, so increasing the temperature shifts it to the right. Sometimes the endothermic reaction is backwards, so increasing the temperature shifts it to the left. The final thing you need to know about for this is if you increase concentration of a reactant, which way does the equilibrium shift? So same examples of equations we looked at before. If I'm increasing the concentration, so I'm putting more nitrogen and hydrogen in, it will shift to the right and it will increase my concentration of product, and I will have a higher yield of product. And that is following Le Chatelier's principle because it's counteracting the change. I've put more reactants in, I've increased the concentration. So by shifting to the right and making more of this, it decreases the concentration of this back towards the original level. Same here, if I increase the concentration of this, then I will increase the concentration of this to decrease that and counteract the change to the system. Notice both these reactions are quite different. Doesn't matter what the equation is, it will always be increasing the concentration of reactant increases the yield of product because it shifts to the right. And the same effect can be achieved by decreasing the concentration of product. So if I decrease the concentration of the product, then the system would want to make more product, so it would shift to the right. So both increasing concentration of reactant, decreasing concentration of product will shift equilibrium to the right. If I instead increase the concentration of product, so increase the concentration of product, the system wants to decrease that concentration, so it will shift to the left and the yield of the product will decrease. So to summarize, you've got the concentration of product and reactant effect. You've got shifting it, increasing the temperature shifts it in the endothermic direction, increasing pressure shifts it towards the side with fewer moles. So if I take this system and I increase the pressure, I've got fewer moles on the right, so that will take me to that system which has a lower pressure.